The monitoring of the Stromfield Magnetar-Like Pulsar PSR J1846-0258 using the Neutron Star Interior Composition Explorer, NICER, from March 2017 to November 2021, including a coherent solution throughout an outburst in August 2020, is discussed in this research paper. A large spin-up glitch of magnitude dn, nu equals 3 × 10⁻⁶, was detected at the start of the outburst, accompanied by a pulsed flux increase of more than 10 times the quiescent level, similar to the 2006 outburst. The flux was rising prior to the outburst, with several sharp rises observed following it, returning to quiescent levels by November 2020. The pulse profile changed shape during the outburst, returning to the pre-outburst shape by 2021. Spectral analysis shows that the flux increases result from a new black body component that gradually fades away, while the power law remains constant. Joint spectral analysis with NuSTAR data confirms this. The paper discusses the Magnetar-Like outburst and the transient thermal component in the context of both pulsar-like and Magnetar-like models. The research focuses on the long-term monitoring of the rotation-powered pulsar, RPP, J1846-0258, which experienced a Magnetar-like outburst in August 2020. Located in the KES 75 supernova remnant, it has a compact pulsar wind nebula surrounding it. The spectral energy distribution, SED, is similar to that of PSR B150958, peaking around 110 MeV and declining above 30 MeV. However, unlike B150958, J18460258 is radio quiet and classified as a MeV pulsar. The paper describes data reduction and analysis from the Neutron Star Interior Composition Explorer, NICER, and Nuclear Spectroscopic Telescope Array, NuSTAR, missions. NICER monitored J18460258 from May 23, 2018, to November 13, 2021, with data gaps due to visibility constraints. NuSTAR observed the pulsar during its 2020 outburst and a quiescent state. The study reports on the Magnetar-Like outburst of August 2020 and its aftermath, including a large spin-up glitch, and discusses implications for understanding the RPP-Magnetar connection. The authors present an analysis of the 2020 outburst of the Magnetar J1846-0258, focusing on NuSTAR and SWIFT monitoring data. The NuSTAR data were reduced using the standard data reduction process, and on-source spectra were extracted from circular regions of 1-foot radius centered at the source position in the 370 keV energy band. The source spectra were grouped using the GRPPHA tool, ensuring a minimum of 25 counts per spectral bin. The SWIFT monitoring campaign provided data on the spin behavior of J18460258 during its quiescent state before the 2020 outburst. The authors analyzed the monitoring data collected between September 17, 2016, and November 19, 2018. On August 1, 2020, the SWIFT telescope reported a short-duration flare in the BAT detector from J18460258, triggering 2 observations with NICER. The pulsed count rate in the 2.510 keV band had already increased by a factor of 4 with respect to the quiescent level during the June 26, 2020, observation. The July 25, 2020, observation showed an even larger, 10 times higher, 2.510 keV pulsed count rate than the pre-outburst value, indicating that the source had already gone into outburst between May 27, 2020, and June 26, 2020. Figure 1 displays the 2.510 keV pulsed count rate from the OUT2 observation on May 27, 2020, through the outburst until the count rate reached near quiescent level on November 22, 2020. The SWIFT BAT burst announced on August 1, 2020, is marked by a vertical dotted line, which occurred after the first recorded rate peaked on July 25, 2020. During the 2 observations, at least 3 more count rate peaks were recorded, with the highest level reached on August 21, 2020. The authors also reference radio observations with the Green Bank telescope and X-ray observations with Chandra of J18460258 in its pulsar wind nebula following the 2020 outburst. These observations revealed a softer power law index and the appearance of a thermal component in the X-ray spectrum. The timing analysis, an extension of earlier work, used data from NICER and SWIFT monitoring observations to compare the quiescent and outburst states. The analysis yielded phase-coherent timing models, accurately describing the rotation behavior of the pulsar as a function of time and tracking the spine volution of the source. Researchers conducted a timing analysis of the Magnetar-Like pulsar J1846-0258 using data from the Neutron Star Interior Composition Explorer, NICER, and the Swift X-ray Telescope, XRT. The pulsed count rate of J18460258 from NICER data, taken between June 26, 2020, and November 22, 2020, reveals a quiescent count rate level and the date of the Magnetar-Like burst detected by SWIFT. Energy-resolved pulse phase distributions, or pulse profiles, were created using timing data from both instruments, enabling the study of the pulse shape as a function of energy for any emission state of the pulsar. These models separate the pulsed emission component from the total emission, including contributions from the surrounding pulsar wind nebula, PONE, and supernova remnant, SNR, and the pulsar itself. The timing analysis began with the conversion of spacecraft arrival times to solar system barycentered times using the instantaneous spacecraft ephemeris, solar system ephemeris, and accurate location of the pulsar. This barycentering process was performed for SWIFT XRT observations between September 15, 2016, and November 19, 2018, and an equivalent procedure was used for NICER observations. From the barycentered event lists, pulse arrival times, TOAs, were derived, and phase-coherent timing models were constructed covering a approximately 4.5-year period from April 28, 2017, to November 14, 2021. The results are listed in Table 1, consisting of 8 separate models, 4 covering the pre-outburst episode, 3 covering the outburst period, and 1 covering the post-outburst era. These timing models enable the study of the pulsed flux as a function of time, probing the outburst, and the separation of the pulsed emission component from the total emission. The required net exposure times for detecting the timing signal of J18460258 above 3 sigma were typically 1520 kiloseconds for SWIFT XRT and 58 kiloseconds for NICER, depending on the instantaneous background rate. Phase-coherent ephemerides for PSR J1846-0258, derived from NICERXTI and SWIFT XRT data, span from April 28, 2017, to November 14, 2021. The dataset comprises pre-outburst, outburst, and post-outburst entries. Notably, the spin evolution of J18460258 since its discovery is illustrated in Fig. 2. Revealing multiple timing discontinuities. Specifically, a clear glitch in the spindown rate occurred just before the 20,162,017 SWIFT monitoring data gap. Subsequently, phase coherence loss was observed during the 20,172,018 SWIFT monitoring data gap. A small glitch emerged in July 2019, followed by a strong glitch in May 2020, which marked the onset of the 2020 outburst. Phase coherence loss occurred again during the NICER 20,202,021 data gap, culminating in a small glitch in July 2021. These events are crucial in understanding the pulsar's spin evolution, highlighting the significance of timing glitches and phase coherence losses in this context. The spin frequency evolution of J18460258, a neutron star, from its discovery in 1999 to 2021 is presented in Figure 2. Showcasing 2 prominent glitches in 2006 and 2020, along with an accelerated spindown rate feature around 20,162,017. A linear fit to the spindown rates yields an effective evolution of the breaking index, n, which indicates a value of 2.7 plus or minus 0.2 before the outburst. The breaking index decreased to 2.16 plus or minus 0.13 after the 2006 outburst but returned to its pre-outburst value between 2006 and 2020. The pulse profile evolution of J18460258 is also investigated by applying timing models to obtain pulse phase distributions for different energy bands and epochs. The pre-outburst period is divided into 2 parts, corresponding to SWIFT and NICER monitoring, with the resulting phase distributions shown in Figure 3. Pulse phase folding of 51 Swift observations and NICER monitoring data reveals a significant pulse shape, especially in the 2.510 keV band. New star observations during the Swift monitoring period confirm the well-known pulse shape up to 60 keV. The post-outburst period, comprising solely NICER monitoring observations, exhibits pulse phase distributions similar in shape and strength to the pre-outburst NICER distributions, as shown in Figure 5. The neutron star J1846-0258 exhibits distinct pulse profiles during various stages preceding and throughout the 2020 outburst. Observations from Swift, NICER, and NuStar reveal energy-dependent pulse profiles, as illustrated in Figure 3. In the quiescent state, the 1–2.5 keV band displays weak pulsed emission, primarily originating from events with energies between 2–2.5 keV. During the outburst, a strong soft pulsed emission component emerges and gradually diminishes, as evident in the NICER 1–2.5 keV light curves. The pulsed significance in the 1–2.5 keV band decreases significantly, from 31.5 sigma to 6.0 sigma, across the outburst segments. The 2.5 to 10 keV and 3 to 10 keV bands also exhibit a fading evolution, characterized by a prominent shoulder or bump during the initial segment of the outburst. Pulse phase distributions indicate an underlying enhanced DC component that fades away. In contrast, the pulsed emission above 10 keV remains relatively constant throughout the outburst. These findings provide valuable insights into the complex emission mechanisms of J1846-0258 during its 2020 outburst. The research focuses on the pulse profiles and spectral evolution of J18460258 during its 2020 outburst. Pulse profiles observed by NICER and NuStar exhibit significant changes in shape and intensity below 10 keV across different outburst phases, more pronounced in the soft X-ray band, 0.53 keV, and less so in the hard X-ray band, 310 keV. The study reveals J18460258 was already an outburst before the detection of a Magnetar-like burst, triggering the NICER Target of Opportunity program. Several reflarings are visible, including one on August 21, 2020, detected in a contemporaneous NuStar observation, demonstrating the validity of the event. This feature resembles a mini-outburst, a phenomenon first introduced by Kuiper et al. In the study of the high-energy characteristics of Magnetar 1E1547.05408. The quiescent state level is reached near MJD 59175, marking the last NICER observation before the 20,202,021 data gap. Spectral fits on the pulsed component were carried out, treating photons collected during off-pulse phases as background and subtracting them from the on-pulse spectra. Joint fits of NICER and NuStar spectra at 4 epochs used the TBABS model to determine the physical properties of the pulsar's emission and its variability over time. The 2020 outburst of J1846-0258 is investigated through a comprehensive analysis of pulse profiles and spectral evolution in the X-ray band, leveraging NICER and NuStar observations. The hydrogen column density, NH, and its spectral implications are scrutinized using a two-component model, comprising a hard power law and a soft blackbody, with linked parameters across datasets. The results reveal a consistent photon index of approximately 1.2, indicating that flux variability is primarily driven by changes in the blackbody component. A detailed examination of the soft X-ray band using NICER data reveals a decline in overall flux and a concomitant increase in blackbody flux during a mini-flare. Notably, the power law flux remains constant throughout the observation period, suggesting that the outburst is dominated by the enhancement of surface emission. This finding has significant implications for our understanding of the underlying physical mechanisms governing the outburst behavior of J1846-0258. The employment of a two-component model enables the disentanglement of the spectral evolution, highlighting the critical role of the blackbody component in flux variability. The consistent photon index of 1.2 underscores the importance of considering the interplay between the power law and blackbody components in understanding the X-ray emission of J1846-0258. Overall, this study provides novel insights into the spectral properties and outburst mechanisms of J1846-0258, shedding light on the complex physics governing these enigmatic events. PSR J1846-0258, a magnetar, exhibited an X-ray outburst in August 2020, following a 14-year quiescent period since its first recorded outburst in 2006. NICER observations provided continuous monitoring of the source before and after the outburst, revealing a flux increase above the quiescent level by late June 2020. The outburst itself saw a more than tenfold flux increase, in contrast to the 2006 outburst, which had a fivefold increase but with less dense sampling and lost timing coherence. The high cadence observations enabled the resolution of rapid changes in the pulsed flux, highlighting the significance of such observations in understanding magnetar outbursts. The 2020 outburst's flux evolution differed significantly from the 2006 event, with a more gradual flux increase preceding the outburst. This contrast underscores the importance of continuous monitoring in capturing the complex behavior of magnetars. By leveraging NICER's high time resolution data, the study demonstrates the value of high cadence observations in elucidating the physics underlying magnetar outbursts. The results provide new insights into the mechanisms driving these enigmatic events, emphasizing the need for continued monitoring of magnetars to better understand their behavior. PSR J1846-0258, a unique source exhibiting dual characteristics as both a rotation-powered pulsar and a magnetar, has been studied during two distinct outbursts in 2006 and 2020. The observed spectral evolution of the pulsed emission, captured by NICER, reveals similarities between these outbursts, including spin-up glitches, transient thermal components, and flux decay over several months. Notably, the 2020 outburst was accompanied by a change in the X-ray pulse profile, which was not observed in the 2006 outburst. The pulsar-like model proposed by Harding and Kalapotharikos, 2017, suggests that the lack of radio or JV emission from PSR J1846-0258 could be attributed to geometry, with MeV pulsars being part of the young rotation-powered pulsar population. These pulsars have global dipole magnetospheres that are nearly force-free, emitting radio from magnetic poles and gamma-ray and non-thermal X-ray emission from the current sheet outside the light cylinder. However, the quiescent behavior and outbursts of PSR J1846-0258 can also be interpreted in the context of a magnetar model, involving different physical mechanisms for emission. The source's unique characteristics, such as its dual nature and unusual lack of radio or JV emission, make it an intriguing subject for further investigation. This study contributes to the ongoing debate on whether PSR J1846-0258 is a rotation-powered pulsar transitioning into a magnetar or a magnetar masquerading as a rotation-powered pulsar, emphasizing the need for continued research to understand its emission mechanisms and nature. The analysis of NICER observations for the magnetar J1846-0258 focuses on quiescent X-ray emission, presenting two distinct models to explain its origin. The synchrotron radiation model suggests that this emission arises from electron-positron pairs near the current sheet, with the spectral energy distribution derived from the smoothly falling spectrum of these pairs. In this model, magnetar-like outbursts are attributed to the appearance or change in a toroidal surface magnetic field component, leading to increased particle acceleration and pair production. On the other hand, the resonant inverse Compton scattering model proposes that quiescent X-ray emission results from particles accelerated by field twists scattering thermal photons from the hot neutron star surface. This model does not predict JV emission due to photon splitting and pair production above 1 MeV. Outbursts in this model are typical magnetar bursts, caused by crustal motions and increased magnetic field twists. Both models provide valuable insights into the complex processes occurring within and around the magnetar J1846-0258, shedding light on the mechanisms behind its quiescent and burst states. Further research is needed to determine which model better explains the observed phenomena, and to explore the implications of these findings for our understanding of magnetars and their role in the universe. The implications and future directions for understanding neutron star PSR J1846-0258, which exhibits both pulsar-like and magnetar-like behaviors, are explored in this section of the research paper. The authors suggest that J1846-0258 may be part of a continuum of neutron stars between RPPs and magnetars, as indicated by its enhanced quiescent thermal emission and other high BRPPs. They also note similarities with transient anomalous X-ray pulsars and the existence of a wind nebula around the canonical magnetar Swift J1834.90846. The authors propose that J1846-0258 could be evolving towards the magnetars, with its breaking index decreasing by 18% after the 2006 outburst, possibly due to an increase in magnetic field strength. However, it is also possible that such sources are born with stronger magnetic fields that are in the final stage of decay. To fully understand its true nature and place in neutron star evolution, continued X-ray monitoring of J18460258 in expanded spectral coverage are deemed crucial. The paper concludes by acknowledging the support received from various organizations and facilities, including NASA, the National Science and Technology Council in Taiwan, and the use of specific software packages like HEASoft and XSpec. Magnetars, a type of neutron star, are characterized by their extremely strong magnetic fields and high variability in their radiation. X-ray observations of magnetars are crucial for understanding their physical properties and behaviors. Previous studies have proposed various models to explain their behavior, including the Beloborodov, 2013, model, which suggests that magnetars could be the result of supernovae explosions, and the Blandford et al. 1983 model, which describes the formation of neutron stars through the collapse of massive stars. X-ray observations of magnetars, conducted using telescopes such as the Chandra X-ray Observatory and the XMM Newton telescope, provide valuable insights into their surface temperature, magnetic field strength, and spin-down rates. These observations are essential for understanding the relationship between magnetars and other astrophysical phenomena, including supernovae, black holes, and gravitational waves. Studies have suggested that magnetars can be associated with supernovae, as seen in Gavriel et al. 2008, and Kumar and Safiharb, 2008. Additionally, magnetars may be related to black holes, as proposed by Harding and Kalapotharikos, 2015, and could play a role in the production of gravitational waves, as discussed in Gorguliatos et al., 2016. The observed variability in magnetar radiation can be explained by various models, including the twisted magnetosphere model, which suggests that the magnetic field lines in a magnetar's atmosphere become twisted due to the star's differential rotation, leading to particle acceleration and radiation emission. Another model, the internal heat budget model, attributes the variability to changes in the internal heat flow within the neutron star. Despite recent advances, current research has limitations. Future studies should focus on obtaining more precise measurements of magnetar properties and developing more sophisticated models to explain their behavior. Further investigations into the connection between magnetars and other astrophysical phenomena could provide valuable insights into our understanding of these enigmatic objects.